Hey guys, gymterm3a walkthrough, and also actually 3b walkthrough. We're going to go ahead and do both midterms in this video, just to save a little bit of time on my end and your ends. Okay, midterm 3 is coming up, final midterm of the year, final midterm almost ever. And I say almost because there's technically a final, but in terms of a midterm, right? This is the very last OChem midterm. So applaud yourselves applaud yourself a little bit, give yourself a little pat on the back. Having made it this far. It's been such a long year, right? It almost feels like a decade ago that some of you started back in a series class. So, it's a good thing to look back and reflect on. But anyways, almost there at the end. I know this is a very stressful but exciting time. To use this exam as a motivation to get done, right? Almost done, almost about to finish, be done with OChem for almost forever. For some of you, we see a little bit more, but for most of you, it's going to be the last time you ever have to put organic molecules together. So something to look forward to. As I mentioned, we're going to do both midterms in this video. So just, because I don't really have time to make 2 videos this time, and I think you guys would appreciate just having everything done in one. So goal for today, we're looking at an hour and a half. I know that's a very, very ambitious goal, but I really want to hope for that. Otherwise, 2 hours, I don't think it's a bad idea, but let's aim for that hour and a half. So looking at that clock like a hawk, right? And trying to finish very, very on time. Okay. As always, we're going to do a little bit of review at the beginning. But we're going to be very, very quick with it. I'm hoping for no more than 45 minutes, which is not impossible, actually. Both these sections are pretty quick to breeze through. So we'll mainly focus on reactions and anything we don't talk about specifically. Look, we have 20 particular products we can talk about anyways. So no big deal, right? We'll get through it. Yeah, cool. Without further ado, let's just get right into it. Let's start talking about chapter 23, the ester enolate chapter. So back in chapter 19 and 20, specifically chapter 20, right, we had a little bit of discussion on the acyl group, right, particular halide and hydride ester amide. And so we talked about the ester a little bit. And one thing I might have said, just a whisper, is that actually, although esters can act as electrophiles, this proton here is of particular interest, right, the alpha proton. It's a pKa of around 25. And with some bases, we can pull it off with relative ease. So imagine like LDA, right? That will let's use a different color here. Right, go ahead and pull that bad boy off at the ester enolate as such, okay? And so we talked about how, if you wanted to, you could alkylate at the center, although you have to be very, very careful with your choices of alkylation agents because it wasn't methyl primary, isn't going to really work out, right? Secondaries are just going to eliminate. And if you wanted to, halogenate, you could do that too. You could open epoxides, right? Stuff like that, yada, yada, right? It acts like a normal enolate, how a normal enolate would, okay? Now, one thing we really didn't talk about back in chapter 20 was, well, wait a minute, right? Chapter 20 is all about the acylation, right? So for example, acyl halide and hydride, they were acylating agents. And we talked a whole bunch about how if I take a nucleophile, right, and I introduce some acyl group to it, right, where X could be anything, that nucleophile should end up acylated at the end. So why was it that we never really talked about ester, right? Technically, ester enolate is a nucleophile. And if I were to, put an acyl group in front of it, it should theoretically go ahead and attack, right? I'm doing these sort of revised arrows here, right? The addition, elimination of the X group, whatever it is. And so essentially we should be able to form acylated enolates, or in this case, beta keto ester. Okay. So why was it that we never talked about it? Well, because chapter 23 is all about this beta keto ester. It's very, very intense and loaded nucleophile that this is. Now, the identity of the acyl group does matter, right? We can't just use anything. Turns out if you use an acyl halide, it's an acyl halide or an anhydride, these guys are a little bit too juiced up, too electrophilic, that in fact, instead of attacking on carbon, right, we get attacks on oxygen. So we get O acylations into these enol acetate type molecules. So not exactly what we want. I mean, they look cool, but not exactly what we would want. Okay. So instead of worrying about, acyl halides and anhydrides, the most electrophilic, but problematic acyl agents, turns out esters will just attack themselves. And so if I take this ester enolate, let's make it first. So now I'll just use a base, right? You can use LDA, that's totally fine. LDA is kind of like, the last resort though. Very, very strong base, does a complete deprotonation on an ester. You can also use weaker bases, like alkoxides, like this methoxide. And out we get out is a little bit of this ester enolate, okay? Now, very good question to get is, well, wait a minute. You just told us that the pKa of this proton is 25. So why is an alkoxide, which is usually around 17 or even 16, able to deprotonate this proton? Well, here's the thing. Keep in mind that deprotonation's pKa is a 50-50 point. So just because something is not truly like really high above or really high above. So the fact that this base is not really high above this proton does not mean that it can't deprotonate it. It just means that it just won't do it completely, right? It's an equilibrium. So, a couple of these alkoxides will eventually deprotonate these esters, right? It's a very mild condition in that sense. And so deprotonation can occur. The other thing is that in reality, you only really need about 1 in 1,000th of a deprotonation to get the reaction rolling because of Le Chalier's, right? Once a little bit of these guys start to form, right, what'll end up happening is this small population of ester enolate will start attacking itself, right? It'll start attacking the electrophilic form of the ester, forming the tetrahedral intermediate that we knew so well in beer back in chapter 19 and 20. Okay. And mechanics still stay the same, right? In that when we form that tetrahedral, minus comes up, shoots back down, and kicks off our only acceptable leaving group at the time, which is the methoxide group. So out we get is the acylated ester enolate, or the beta keto ester. And remember, when that methoxide leaves, right, it is not a good leaving group. So how does it stabilize afterwards? Just like with ester hydrolysis. Remember, ester hydrolysis. When we form that carboxylic acid, and we had that O minus, what did that O minus do? Deprotonated a proton to stabilize itself. So we're going to do the exact same thing here. But instead of deprotonating on an acid like an OH, what we deprotonate is on the proton in between the keto and the ester. Okay, that beta proton. Sorry, should I keep consistent here with the different colors? So after a little acid workup, right, end up with the beta keto ester. Okay. So this here, the acylation or the self-condensation of an ester is known as the Claisen condensation. Okay, and it's sort of the sister reaction to the aldol, right? You might remember the aldol was when we had like a ketone, right, or an aldehyde specifically, right, attacking one of itself and condensing into an enol, right, or aldols first. So first it forms an aldol, okay, and so aldol type condensations. So when aldol type carbonyls, or we're doing aldol type reaction, it's usually when your electrophile is like an aldehyde or a ketone. Claisen is a carbonyl condensation where the electrophile is an ester. right? Because it facilitates that addition elimination that we see on acyl compounds. Okay. Now, a couple of things to know about the Claisen condensation mechanism. For one, this deprotonation, very, very vital, right? As you can see here, we have 2 protons that we have to deprotonate. So generally speaking, every single Claisen requires 2 alpha hydrogens, absolutely required. Okay, so if you want to condense 2 carbonyls, right, or 2 esters in particular, got to have at least 2 alpha hydrogens. Okay, so esters like this have really no business doing Claisen condensation. Okay, because if I were to draw the product, that condensation, it would look like this, right, where the O- has no way of deprotonating to stabilize itself. So if it can't deprotonate, it's going to go ahead and reattack and do what we call a retro Claisen. It's going to just turn backwards. Okay. And a very good way of recognizing this is looking for these tertiary type centers. Okay. A couple of you might be thinking, how in the world did you draw that product so fast? I'll show you a trick in a second. How about to do these in 2 seconds? Okay. So one thing to notice is that Claisen condensation very much requires 2 alpha protons. And that's always something you should look out for, right? The nucleophile has to have 2 protons. So look right there, make sure that those are available. Sometimes you'll have questions where, it may seem ambiguous as to who will attack, but it's actually not, as long as you know that rule. Okay. Cool. The other thing to note is, again, this idea that we're using a weaker base, an alkoxide, but very particular alkoxide, right? The alkoxide matches the ester. Why is that? Well, remember that alkoxides, esters, can also attack on the ester to do sort of a transesterification type process. So, for example, let's say that I used an ethoxide. Very high chance that instead of having the methyl ester, we'll have the ethyl ester. A couple of you might be very quick to say, well, wait a minute, Cooper, you always told us that acid base is faster than substitution, and that is very true. But keep in mind that the acid base is already fighting a thermodynamic hill, right? The alkoxides are already stronger acids or weaker bases than the ester itself. So already we're trying to fight this battle of deprotonate the proton when there's also this very nice electrophilic center that this guy can attack, much more likely and much more willing to do so. So always make sure your alkoxide are matching your esters, right? Because otherwise you're going to end up with esters that you didn't want. Okay. Although we'll kind of see that this is not the biggest deal in the world, but it is still an important thing, especially if you need to retain that ester. Sometimes you don't, though, and we'll see what I mean by that. Okay. Cool. So again, if you take any ester really, for example, an ester like this one, and so long as you match the base, right, maybe give it a little bit of heat, not that you need to, you'll get the Claisen condensation. So what's the fast way of trying this? The way that I do it is I take one of these esters. So for example, in a Sel's Claisen, one of these esters, the alpha carbon, the group that's on it, I just kind of draw it underneath like this. On that alpha carbon, I draw the acyl group of the ester, and that's all there is to it. Okay, so I take that acyl group and I just kind of put it right here. Remember, the point of the Claisen is that it is an acylation of an enolate. So if you're acylating the enolate, you're just adding the acyl group from the ester onto the enolate, right? That's it. So you're just getting rid of that leaving group and you're just adding the rest of it on there. It almost is, I mean, not that this is the correct mechanism, but a way to think about it is it's kind of like you're doing an SN2, right? It's like you're doing an SN2. So you're adding this whole group onto that nucleophile. Okay. Doesn't matter how complex this gets. Right. So long as we have those 2 alpha protons, we have a base that matches the ester, right? We can do self-condensations. So again, just all that acyl group just right here. I'm going to do a lot of abbreviations. One of my favorite abbreviations for rings of any size, of any type, is I just draw a circle, a literal ring. Okay. Cool. Now, we can also do mixed glycines. It's totally possible. It's the same rules as aldol, right? If I'm going to do a mixed glycine, I need to make sure that I don't have, a competing nucleophile. Because imagine if I try to condense these two guys, right? A and B, right? A and B both have two alpha hydrogens, very likely nucleophiles. We'll get AA attacks, AB attacks, BA attacks, and BUV attacks. So, you make four things, you're actually really making nothing. You'll maybe at most 30% total yield of some product, and it's just varying percentages of these guys. So very, very bad reaction. So how do we prevent this? We just use esters that have protons, right? That have those two protons on them, and esters that don't have any protons on them. So for example, benzyl ester. Now, benzyl ester itself is a very resilient ester, but no protons, so eventually this guy will attack there. Okay, so eventually this anion will, muster up the power to attack there. And so what we'll get, again, is an acylation of that alpha center. So all that right there will just go right here. Just like that. Nothing too crazy. Some famous partners, non-analyzable partners. Formate ester. Okay. The carbonate. Trifluoromethyl ester. Okay. And I'm trying to think of any others. I think that should be good. Yeah. I can't think of any other ones. So we'll just keep it to that. Oh, actually, no, never mind. Take that back. There's one more. There we go. This ester here. This is actually an oxalate. Okay. Now, if we look at these groups here and we think about what is that we're adding to the enolate, what are we acylating on the enolate? For two of these is very obvious, right? We can see here, we would just acylate here, and see here, we just acylate here. So you can see the ketone that would form, and this would actually give an aldehyde. So this is a very good formulating agent. Okay. But these two might seem a little weird at first as to what exactly you're adding. But again, if we just use that logic of we're just getting rid of one leaving group, everything works out. We're essentially just, not acylating, we're esterificating, I guess. So we're adding an ester to that enolate. And in this case, we're adding a ketone with an adjacent, an adjacent ester. I apologize, I'm talking quietly because, as you can imagine, late at night that I'm doing this. Okay. So just to show some examples of this, just so that you guys aren't left in the dark on how to deal with these. For example, this carbonate here, right? All I'm doing is acylating and adding an ester at this position. So beta diester is the product that we are forming here. Okay. If I wanted to use that oxalate, okay, same exact thing, acylating. I just have this guy here, just like that. Okay, nothing too crazy. Cool. So Claisen condensation, just an acylation of an enolate. That's all it is. So for a majority of these, just acylate the ester nucleophile. Okay. Now, as always, you can do mixes. It's totally possible. When you're doing a mix of an ester, of a diester, luckily there's only really one example you need to know because esters can only analyze on one side. So as long as you know this example, you know all of them, right? Both of these have two hydrogens, so either one could attack. But let's say that this guy had this methyl here. Suddenly, right, we have now limited the positions that can attack. So go ahead and do an attack like that. One attacks 2, 3, 4, and 5. Get a 5-membered ring. right? One attack two. So two will be where our acylation occurs. So our ketone forms at two. Three has a methyl. 4, 5 have nothing. If they did, we just add it in. And then one will have the ester hanging out on the side. Okay. So this is our intermolecular Claisen, or what we call a Dieckmann product. Okay. Only way this can change is if this were a carbon longer, right? And so that would give us the 6-membered ring. But again, as long as you know the shape, you know all of them. This is the only shape that a diester Claisen can take form of. Cool. All right. So that is the intermolecular for a Claisen. And again, I mean, nothing can really change this. Just a matter of looking out for your esters. So let's say I had like this here. Right, this is still intermolecular, nothing really changed. I just added, looks like to carbons, what, 1, 2, 3, 3, and 4, just a ring. So again, 1 proton, 2. So this is our nucleophile, attacks right there. You can kind of see how that would form out. Just like that. Super simple. Okay, cool. Now remember, Claisen just means that we're acylating an enolate, right? So the electrophile has to be an ester, right? Because that's our acylating agent. But the nucleophile can be a variety, many variety of things, right? For example, a ketone. So let's say that I have a ketone here, right? And I put it in some base, and I add an ester. Remember, ketones are already a bit resilient to self-condensation. So it's okay that we mix the base in with the ester, or sorry, the ketone, not a big deal. But when we add in our ester here, right? So we add in the ester, yeah, like this one here. The ketone enolate that forms now has a target, right? It has the ester target. So what we'll get is the attack. Again, I'm just going to be a little lazy here and draw all the arrows in one. Don't do this on your exam. I can do it because I've already passed the class, right? But again, we're just acylating that alpha position, just like that. And so now we can make beta diketones. Okay, cool. So keto esters, ketone just attacks the ester. So you can imagine the intermolecular variety of these reactions. Nothing's really too crazy. Okay, again, 2 examples here, but as long as you know these 2, you know all of them. Okay, the first one is when we have an attack like this one. So 1, 2, 3, 4, 5, 6. Oh, okay, so 1, 2, 3, 4, 5. So this will go ahead and attack here. So this is if a endocarbon goes ahead and attacks. Get a 5-membered ring. Okay, where again 2 is where our acylation event occurs. And if there's anything 3, 4, 5, just add it in. 1 is just going to carry the ketone. Okay, so this is our diketone when we attack on a exocarbon. Again, if this were allowing for a 6-membered, it would just look like this. So not much different, just a ring expansion, right, from 5 to 6. Okay, the other example, quite short, right, is if a exocarbon attacks. So if this anion attacked here, right, that would result in, right, 1 attacks 2, 3, 4, 5 if they had something added in. 6 now has the carbonyl. So we have sort of this internal diketone, right? So it actually looks a little funny. If you think about it, it kind of looks a little like Shrek. So Shrek's diketone, I guess. Anyways, so that's what that shape looks like there. Okay, cool. So that's all there is to it, right? You have 2 esters, condense them, right? You have an ester and some nucleophile, condense them. Okay, just keep in mind these partners here, right? General partners. Again, anything qualifies. Again, like a phenyl ester qualifies as well, as long as the other partner does not have the appropriate number of protons. You can almost even get away with what we talked about earlier, where if we have, oh, I guess I had here, right? Where we have a diester where one doesn't have enough protons to, to finish out the reaction, right? So technically, this here could also be a good partner if you wanted it to be, so long as you have an ester that can analyze, right? This guy can go ahead and acylate. As such, right? Totally possible. Okay, cool. All right. So what's the point of making these diester compounds, right? Why do we do it? Or these beta keto ester, these dicarbonyl compounds? Well, these dicarbonyl compounds, like we just discussed, have this very acidic proton on this alpha position. So a base can, with relative ease, take it off. No need to heat it, just add the base in. And this anion here, right, pKa-wise, particularly acidic, right? For the beta keto ester, a very good value to know is around like 11. Okay. If you think about a diketone, which has two ketones, so remember back in chapter 19, chapter 20, ketones are more acidic than esters because esters have this one donating group on them by resonance, so it conflicts with the anion. So this diketone, its proton is around like 9 or 10. Let's put 10 on it, right? Again, absolute value doesn't mean anything. It's the relative value. So the fact that this is more acidic than the ester is all that matters. And so you can possibly imagine if there was a diester compound, right? Still acidic. It's still acidic, right? But it's going to be the least acidic of all of these because it's made of two esters. So like 12, that's a good value. I think actually this is like 13 and this is like 9. So things like 9, 11, and 13 reminds me of a national tragedy. But anyways, this proton, particularly acidic, right? It's about the same, right? 11 is about the same as a thiolate. So if I take a sulfur and protonate it, and back in 118A, we learned that thiolates are very, very good at doing like SN2 type reactions or alkylation type reactions. So if I wanted to do, let's say that alkylation I did earlier, right, on the ester enolate, right, this works remarkably well. And not only can we do this on primary methyls, right, the OG SN2 substrates, but we now open the door to secondaries because this is such a weak nucleophile, or sorry, such a weak base, right? This is not an ester nucleophile where we have a pK of 25 and I have to worry about elimination. This is again like a thiolate where the thiolate, very, very low pK, or relatively speaking, it's lower pK than a strong base, right? And has the ability to substitute without any elimination complications. Okay, so we've now opened the door to things that we can add in. Okay, so you can definitely add in R groups if you wanted to. Epoxides, totally, we can add those in if you wanted to. Okay, so essentially what we're doing is we're adding 2 carbons and an alcohol, right? Okay. You can add in carbonyl compounds if you wanted to. Right? It's totally possible. It's totally up to you what you want to do here, right? But all of these things are viable electrophiles that we can add. We've just kind of opened up that library. Okay, so going back to here, right? The alkylations, all those things that we said we could do on ester enolates and ketone enolates and aldehyde enolates, but we had problems with. Suddenly, those problems are gone now that we have a beta carbonyl system. Okay, so now that we have this beta ester, totally more acidic, totally viable, totally free of these byproducts we did not want. Okay, now you have the ability to have 2 protons there. So if you wanted to, you could theoretically do 2 electrophile additions. So I'll just do like something like this. So let's say the first one was like an alkylation, right? maybe we, yeah, let's just do 2 of these. So just add like 2 of these. Maybe this one is secondary. This one is primary. Okay. So we have our alkylations. Now that we have our alkylations set, right, what can we do to finish off this product? Well, an interesting reaction occurs when I heat this product up in acid. Okay, so I heat this up, throw in some acid, something interesting happens. So back in chapter 20, we learned that carboxylic acid derivatives like esters hydrolyze into carboxylic acid. So that's what's happening first. But this beta keto acid is actually very unstable when heated. In fact, when it's heated, something really interesting happens. Okay, the carboxylic acid completely disappears. In fact, it has decarboxylated. Okay. So we can do decarboxylation events on the beta keto acids or the beta keto esters. And so the question becomes, how in the world is that going on, right? Why is it that this is occurring? Well, if I look at a beta keto system, okay, let me actually draw it this way first, okay? One way to kind of understand what's going on here, why is it that we're able to liberate out CO2, is to think about this bond here, okay? The electrons in this bond, okay? If I'm to just randomly lose CO2, so let's say that I wanted to lose CO2 on a molecule, right? If I were just to do that, generally what would have to happen, right? Something takes this proton, electrons go in between C and O, and this bond here breaks onto R. So what we get is an R minus in CO2. Okay? So, I mean, CO2 has no problem existing. It will if it can, right? It's a stable nonpolar molecule. But what really matters is the R minus, right? How stable is R minus that it can exist? Again, if R minus isn't stable, if it isn't acidic enough, if it's not being stabilized, in no way is this reaction going to be favorable, right? Going from the carboxylated species to the decarboxylated species. So if I just kind of think about what's going on here, same kind of idea, right? Why is it that we're able to decarboxylate? Well, let's look at R minus, right? Where do we place that minus? Well, that minus goes alpha to a ketone. It becomes an enolate or an enol, right? It's an allylic system. And allylic systems resonate. So decarboxylation functionally exists. It happens when the electrons in that C bond, right, are able to result in conjugated systems, right, in resonating anions that can exist very freely and very happily. Okay. Now, obviously, we're in acid, so we're not really going to form a enolate here. What we're going to form is an enol. But same idea, right? So you can imagine this is going to pick up that proton. So usually the representation that we see for this reaction is, you swing over that bond, right? Ketone attacks the proton, right? We get this sort of cyclic, pericyclic event going on, which is, I mean, totally viable mechanism. I'm not saying that it isn't, but this mechanism, one thing that it really kind of irks in me or kind of gives up is it doesn't explain why decarboxylation can happen, right? It just kind of shows it, and it makes you feel like the ketone is all you're relying on in decarboxylation, when that couldn't be farther from the truth. The point is that when you decarboxylate, you are forming an anion that is conjugated, that is stable, that is acidic, right? Concept that runs deep in our blood since 118A, right? And so many systems, I mean, we don't need that keto system, right? For example, let's say that I have this here, right? this system can easily decarboxylate, right? If you just heat this up and you don't even need acid, right? Why is it? Because again, let's think about it. If I do that decarboxylation sequence, not only is this anion allylic, right, or benzylic, but it is also benzylic in conjugation with an electron withdrawing group. And in this case, an NO2, much more powerful withdrawing group than a ketone, right? Much more relevant example. Let's say we have this. This is known as a vinylogous ester here. Okay, or sorry, vinylogous beta keto ester, right? Oh, sorry, not this. This here. There we go. Okay. Where again, oops, sorry. When we look at the electrons, right? When we get rid of the carboxylic acid, right? Or let me draw the arrows. So when we do that sequence again, where the electrons come here, well, let's just take the step further, right? The electrons can still sink into a ketone through an extended enolate system. Okay, so many systems can decarboxylate, and obviously in this class, because it is run by Dr. Helix, you're only required to know the beta keto system. But what I want you guys to take away from this, because when you take biology classes, higher level biology classes, biochem, decarboxylation, it's not just some strict thing that only happens in one system. It occurs in many types of systems. Yeah. And it all depends on the electron flow. For example, an example that I was looking at from our own chemistry department, Dean Tantio. I don't know if he's still on this project, but he was looking at these kind of decarboxylations. I was looking at a decarboxylation that looks something like this. Okay. I forgot the name of these guys. They're like carboxy. So this here is the so this here is the benzisoxazole. And he was looking at these, let's look at these carboxylated species. Okay? And so when you look at this, right, you would think, oh, that's a pretty stable carboxylic acid. Turns out this will carboxylate actually very, very easily. Okay. And so one way to think about it is again to kind of think about where those electrons can flow, right? The electrons can flow here and eventually sink onto this oxygen. Which maybe it seems obvious to me, maybe not to you guys, but still pretty cool thing that can happen. Okay. And so you can form these nitrile oxide species. Where if you look again, this is that same, it's a phenol, it's a phenolate, which is para to an NO2. So highly acidic. Okay. So broad message here is don't think of just beta keto systems. Yes, that's the only thing required for the class, but anytime you have an ester an acid or any kind of derivative that is able to hydrolyze into an acid that is conjugated, or its bond is conjugated to a resonance system, to an EWG, highly probable that it can decarboxylate. Okay, so let's take that little point there that I just made, right? Why did I say that anything that can turn into a carboxylic acid? Well, keep in mind that esters are not the only derivative, right? There are so many derivatives, right? Like there are amides, right? Amides are able to hydrolyze, although very, very difficultly. Nitriles, in fact, nitriles are very much like esters. You'll see a lot in the book and in the practice problems that anytime you see something an ester can do, a nitrile can do it just the same, okay? To put into perspective, the alpha proton of a nitrile is the same as an ester. These both clock in at about 25. So these guys do the same job, right? They're hand in hand together, able to do the same things. Okay, cool. Sorry, I rambled a little bit. So let's kind of get back onto track here. Okay, cool. So going back to the point, essentially these beta keto systems, right? Once you've added on their alkyl groups, whatever you want them to be, right? You can essentially get rid of the ester, make it disappear, and what you get are these alpha substituted acetones, right, or ketones. And so this is the primary tool of the beta keto ester, right? Remember, if I took a ketone and I tried to do an alkylation instantly on it, right? So many problems that could occur. One being that the alkylation won't even happen, right? For example, like if I try to add in like this phenyl, or sorry, this benzyl halide, possibly that, this won't even work. Sometimes you'll also even get over-alkylation. You guys might remember that. Over-alkylation is a pretty big issue. So what's the solution? The solution is you acylate the anion. So base, and then, so if I want to go to a keto system, a beta keto system, I add in the carbonate. Right? So I add in carbonate to get the beta keto system. I do my alkylation now, which now very likely will happen with ease. And I can just decarboxylate and make it seem like that ester was never there in the first place, right? It functions as an auxiliary to make the reaction easier. And then once I don't need it, I just get rid of it. Oh, what in the world just happened? There we go. Yeah, cool. All right. And I have this now branching center that was, now available to me because of my ester, of my beta keto ester. Okay, cool. Now keep in mind that you do need a derivative. So obviously if you have a diketone, good luck decarboxylating anything off of that, right? This is not going to work. But if I have, let's say like a diester, that's two esters. So I'll have two of these carboxylic acids that can, one of them can go ahead and decarboxylate. And so I can also make substituted carboxylic acids. Okay, cool. So in synthesis for chapter 23, when you're thinking about, when I have to use a Claisen condensation, how can I tell what I need to do next? How I need to move on, how do I move backwards? One of the best things you can do, especially if it's like a ketone or again, like a carboxylic acid, right? Is you can look at your ketone and think, okay, well, the whole point of this chapter is I can alkylate on these alpha centers to make these branching centers. And I can think, okay, on this ketone, there must have been an ester before. So I think that a decarboxylation event occurred. And so I want to add in an ester. Now, where do we want to add in the ester? Again, if the whole point of the keto is to make alkylation easier, then you want to add it on the branching center, right? So I'll put E here for ester, or actually I'll just draw it out, right? We want to go ahead and add in our ester on that side because again, it's these groups here that were again added, made possible to add because of that ester back in the past. Okay. Now again, we can get rid of these esters and say we did like base electrophile sequences times 2 here. Get back to our beta keto ester system, and even our beta keto ester we can dissolve very, very easily, right? Starting from the ester alpha beta, cut between the alpha and the beta, what we get is a beta fragment and an alpha fragment. Okay. The alpha stays the same. The beta we want to add an OR group to, right? Just match the OR to whatever your other ester is. Now, if you usually know you did this right if your ester is the same, so your pieces are the same, you did this right, or you did this right if you have like an ester that has no alpha hydrogens and an ester that does. Okay, that's usually a good cue. If ever either of these things are not satisfied, like you end up with two, like let's say you end up with two esters, one that looks like this and one that looks like this, I would recommend going back to this step, and rather than cutting off both alkyl chains, just cut off one at a time. So for example, let's say that I had this here. So I had let's say that I had this here and I was running to the issue of like, oh, when I actually, we can even do this, right? So let's say that I specifically had like this here and I was cutting off both, right? What ends up happening here is that when I do my alpha beta cut, I end up with two esters that have alpha protons, which is kind of yuck. I don't want that, right? That's not a good proposition, proposal for a Clayson. What I can do is I can go back to here and just cut one at a time, right? So now maybe I choose to just cut this guy off first. Sorry, so I'll do this. So I choose to only cut off, let's say, this guy. And then I have this left, and now I do my alpha beta cut. And when I do that, what I get is this here, which if I did this right, these should be the same now. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. Sometimes what may appear to be an alkylation actually isn't. It was just part of the original ester, but you don't know that until, right? Until you've experienced that or you go through it. Okay, cool. All right. So that's the beta keto ester system. Last thing I'll leave you guys on with is just the oddities of some groups. So for example, let's say that I add in an epoxide. Okay. Epoxides give us alcohols, which you can imagine alcohols can do wonderful things, such as if I just kind of, heat this up a little bit, maybe even just you can throw some base if you wanted to. You don't have to, but you can imagine you can get some lactonization here. So this can kind of, shield the ester a little bit, although you can imagine decarboxylation kind of shred it apart. So sometimes you may not even want to get rid of the ester, right? You may want to just use it to do transformations just like this. That's something you could do if you wanted to. Another one is the Michael acceptor. So the enone, right? The enone, you can go ahead and add in, right? And so it'll look something like this, right? 1, 2, yeah, 2, 3. If you add this in, you can isolate out the Michael accepted, keto ester. But if you put it in some more base, heat this up for a little longer, so you kind of just take what you have and you just heat it up, you can get a cyclization event, right? A Robinson annulation. So 1, 2, 3, 4, 5, and 6. So 2, 3, 4, 5, 6, 1. Like this here. I'm not sure if this was covered in your class though, so if this doesn't seem like it was covered, no worries, right? Nothing to worry about. No big deal. So we'll have an alkene between 1 and 2 here, but you can have this happen. Again, this can decarboxylate, right? If I draw the anion, it is conjugated to the ketone, so definitely a possibility. But I'll put a star here. If you need to know, just need to know. Okay, cool. So just some cool things. Again, because you can isolate this out, you can do chemistry on that ketone if you wanted to. Totally up to you, right? How you want to do things. Yeah, cool. But with that, gonna call it on the beta keto ester. Any oddities, anything else we need to know, we'll just see in the problems. Cool. So last part 23 is just the acyl couplings. So I'm just gonna go through this very quickly. Thiazolium, right? Looks like this. This proton here, very acidic, pK of like 17. Okay. Hydroxyl, I can just pull it off. Essentially what happens here is we get what we call a symmetric coupling of aldehydes. So this is just how I think of it. And you're welcome to think about it however you want to. But you take 2 of these aldehydes and you just couple through, right, the proton there. Just that one of these carbonyls get reduced. So sometimes you'll hear me refer to this or other people refer to this as like a quote unquote symmetric product. And you might be thinking, this is not symmetric, right? It's asymmetric, right? It's a keto instead. But what we mean by that is that the R groups on the keto hydroxy ketone are the same. And this is sort of a call that you're using a thiamine or a thiazolium. Okay, so imagine if you have an aldehyde, this one, and you use thiazolium. So I'll just put thia here. And you just kind of want to copy this chain over. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, cool. Generally don't want to mix two aldehydes together because you don't know who gets attacked, but you can mix aldehydes and ketones. That's totally possible because the thiazolium will selectively attack on the aldehyde, activate this essentially as this anion here. So it isn't exactly this, but it acts like that. And this will tap on the ketone. So you can get some selective coupling. So 1, 2, 3, 4, 5. Oh, still too long. 1, 2, 3, 4, 5, 6. Okay, we'll just do this. Right. So you can get some selective couplings like that with thiazolium, but this is hardly a mix, right? It's definitely more of a it's more of an intermolecular. If you want to couple two aldehydes intermolecular, that's fine. Just it doesn't make sense unless it's symmetric, right? So for example, if you want to couple these two aldehydes, it's totally fine because thiazolium will just attack either one of them and couple it to the other side. So 1, 2, 3, 4, 5, 6. So you'll get this here, right? But if we have like a methyl here, we don't know who attacks and who doesn't, right? So it gets kind of complicated, right? The methyl in this case will either be here or will be here. We don't know. Cool. So that's the whole thing with the thiazolium, right? Makes these alpha hydroxy ketones. And you can imagine figuring out where these come from very easy, right? You just kind of cut through the bond here, ketone or carbonyl becomes aldehyde, and then alcohol also just becomes an aldehyde. So how do we more reliably couple these mixed aldehydes or different aldehydes? You just use dithiene. So I have this aldehyde here, right? I can add this one free dithiene on this, and this proton, not as acidic as the thiazolium, but it's up there, it's 30, right? Take it off with N-bule. Right, suddenly we have pretty acidic anion, and add in again like another aldehyde. So now more reliably form this hydroxy compound. If you want to get rid of the dithiene, you can do so very easily. Just use mercury chloride and water, right? This is the most important part. So if you can't remember, I mean, you have a note card, so just write this down, right? But the water, the mercury chloride part is the important part, okay? But we can go ahead and do these mixed couplings. You could also just completely hydrogenate the center. Usually use rainy. So rainy nickel is what this is short for. But this will just make like an alcohol, right? This is more like a predictive product, not really synthetically useful. Like I don't know how you tell to do this unless you see like a carbonyl disappearing somewhere, right? It's really the only way to see that. Okay, you can also do alkylations if you wanted to. So if you wanted to here, you could N-bule, then like RX. Right, so again, just methyl primary, it's the only stipulation. And then do like in mercury chloride. So you can make ketones if you wanted to. I've never really seen this being used though for this purpose. It's usually just to, protect or to couple, right? Now, one question I get every year is, oh, if the sulfur variant works, can I just use an oxygen acetal? Answer is no, okay? The oxygen acetal turns out actually is not able to acidify this proton enough. Otherwise, we would have just told you to use that, right? The oxygen acetal, so this for oxygen, actually has this at around like 40, which is insanely higher, right? Now N-bule has to kind of, it's a hard fight a little bit harder than it did before to take off that dithiene proton. So please don't use the oxygen acetal. There's some resource somewhere that tells you you can. I'm telling you now you can't. Okay, just don't do it. I can't guarantee that your TAs will be nice to you about having used that. Okay, cool. Now, one method that's not really talked about, and I'm not sure why, because it completely ties in through the whole chapter 23 theme. But one way you can also kind of couple aldehydes together is cyanide. Okay? The cyanide, when we add it in, it makes the cyanohydrin. Remember, I mentioned earlier that the ester proton is very acidic, right? And a proton that's equally acidic is the one next to a nitrile. So taking that information, the fact that we can add nitriles into aldehydes tells us that, I mean, this is an alpha proton to the nitrile. This is now an incredibly much more acidic proton, especially with this adjacent alcohol that can help affect inductively. So much so that something like KOH can pull it off. And effectively, we have an anion that's similar to the one that we see in the diazolia mechanism, where instead of CN, we have a diazolia. Okay. Now, you can add in any aldehyde you want to, for example, like this one here, and you'll get the coupling. And here's the cool thing about this reaction, is that once you've got the aldehyde on, you want, eventually the cyanide just reverses off. Right? Usually if you just add in like some water, just takes it right off. And what we get out is our mixed product. So you can use this one, process as well if you want to, kind of to show off. Totally possible. I'm really surprised it's not taught because it ties in so perfectly to everything we've learned so far. Okay, cool. Oh, one last thing before we finish off on chapter 23. That Michael acceptor stuff we were talking about back here, actually, there's another one too. The cyanide version also exists. I don't know if I just think I'll mention just in case, but this also exists too. So that would make something like that. Yeah, cool. All right. And you can imagine, right, we can hydrolyze that, maybe do some pretty cool stuff here. Like, let's say we hydrolyze. Actually, let's do this here, the malate ester. Right, that would make the diacid like this. No, the triacid actually. So this would turn into an acid, right? No, one more carbon down. 1, 2, 3. Okay. You can imagine one of these will fall off, and now we have a 1, 2, 3, 4, 5, 6. We have a 1,6 diacid that we just heat this line up, might even turn into the anhydride. So, interesting target. Interesting thing to think about. Okay, cool. But with that, we're going to call it on chapter 23. Okay. If anything else we can talk about, we will. But it's already been an hour, and I don't want to spend. I didn't even want to spend this long on this stuff, right? So we've got to wrap it up. All that's left now is sugars. So main focus will be on just going to focus on reactions for sugars just to get through it. Okay, cool. So sugar reactions. One thing to understand about sugar reactions, right? Why does it seem like they don't make any sense? It's because what we're doing is we're looking at the oxidative tests that Emil Fischer, your sugar ancestor, did to figure out the absolute structure of sugars, right? This is what he did, right? This is how he figured out what every structure, what most sugars look like. Incredible feat at the time where he had absolutely no tools, like no NMR, no IR, no CNMR. Imagine how you guys feel now with these tests to figure out structure. Emil had none of those, and he was able to figure out all these sugars, right? And what they look like. Absolute madman, academic weapon. Emil Fischer, he is. Yeah. So enough slobbing over him. But that's the whole point of the first section of sugars, or the reactions, right? What are the tests that he did? Okay. So first test you guys learned, tollins and the felons. Okay. So fairly simple, right? If I have, let's say, like an aldose sugar, for example, this here is D-glyceraldehyde, right? A tollins test, which is like C2OH and O minus, or a felons test, which is silver, okay, and OH minus. I think it's whatever. I don't remember who's who, but whatever, not the point. But anyway, both these guys work in that they oxidize a aldehyde into a COH. Okay, so in response to this, would involve any aldose will generally respond to this, right? As long as you're aldose, you will give a positive response, right? That the sugar has reduced the metal. Okay, so aldoses oxidize on that since you're there. Now, ketoses are a little trickier because, again, a ketose is not an aldehyde. So it kind of feels like it really shouldn't respond at all to these tests. But it turns out it does. It does respond. Right, so let's say this or Ag2 plus or Ag plus, right? Turns out we do get a response. So I'm just going to put here a response. But the response, right, the molecule that's responding, it's a bit complex. And honestly, whoever you talk to will kind of disagree on this. I think that the textbook gets it wrong. I think that it doesn't totally get it right. But the response that I agree with is that the ketone actually turns into its aldose. And this is how it does it, okay? In base, so if I have basic condition in base, you can pull off this proton here to form what we call the ene dialate. Okay, so this here is the ene dialate, or the ene diol. And the ene diol, completely reversible. So you can pull out this proton and just put it back on, right? Just as normal. The other thing that you can do actually though, is rather than forming the ketone or carbonyl at the same position, you can form the carbonyl at the other position. So now instead form it here. And what we get out is the aldose. So what we get out is the aldose. So in basic solution, we call this a base-induced epimerization. Ketoses can transform into their aldose, and it's their aldose that is responding to the test. So ketoses are also reducing sugars, but that really it's their aldose that's responding, right? Because the base is inducing the epimerization. Now, if you learned this, know this. If you didn't, go ahead and skip it. I just don't know. It seems kind of like I haven't gotten a good response as to whether or not you guys have learned this. But anyways, that's the point. Okay, so in base, the ketose can epimerize, turn into the aldose, and respond. Okay, now all of this, right? Again, the sugar is reducing the metal, or the metal is oxidizing the sugar, right? This is the whole idea behind reducing sugars. Why we call this. The biggest point is that a sugar, remember, linear sugars don't really exist, right? If I have a sugar that looks like this, right? With whatever number of these, really spends 99% of its time in its cyclic form, right? So really, when we think of reducing sugars, what we're saying is that the anomeric position, right? Anomeric position is a hemiacetal. So we're looking for an OH directly connected to that carbon. Okay, as long as that's possible, this is a reducing sugar. Okay, whether it's aldose or ketose. But we can do some other oxidation tests to figure out other things. For example, phenolens and toluenes can't tell you if something's a ketose or an aldose. So what can? You can do the bromine water test. Okay, so what's the bromine water test? The bromine water test oxidizes aldose aldehyde into carboxylic acid, or what we call N-aldonic acid. Okay, ketose will not respond to this. It will not respond. And this is not basic, so we don't get that base-induced epimerization into the aldose. Absolute no response. Okay, but aldose will, so you can tell an aldose and a ketose apart from the response from there. Okay, aldonic acids. So when we have the monocarboxylic acid, are pretty interesting species, particularly if you have a couple of these oxygens here. So this here is the aldonic acid of glucose. Okay. How did I know the OH structure of glucose instantly? Well, actually, I messed it up actually. How did I know that I messed it up? here's a really cool trick you can do. If you take your right hand and you make a middle finger, glucose's OHs follow your fingertips. So this is essentially a middle finger with your right hand. And then you can think the aldose part is your thumb. Okay, that's your palm. And then this is you guys studying for the test. Okay. Anyways, but that's how you know glucose off the top of your head. But if you have alderic acids, aldonic acids, heating these guys up will actually force them to cyclize. Usually the 5-member ring prevails, so the gamma lactone, just because of kinetics. It's easier to make, it's faster to make 5. Okay. I like to count the carbonyl as 2, 3, 4, 5. That way, the number that I stop at is the ring size, and then that alcohol on that carbon is the one that's cyclized, that's 1. Okay, so 2 is the acid, 3 has nothing, 3 has an OH, 4 has an OH, and then 5 has a CH, OH, and a CH2OH. Okay, so we can make these lactones here. Okay, so ketosis aldonic acids can respond. Okay, so aldose oxidized by bromine water into aldonic acid, and then aldonic acids can cyclize in heat. Okay, ketosis will not respond to this test. Okay. Both of these, however, will respond to an interesting test. Okay. They will respond to the HNO3 test, which is a complete oxidation. Right, it will oxidize primary alcohols, and it will oxidize the aldehydes. Okay, so this is what we call an alderic acid. Okay. And ketoses don't have an aldose or an aldehyde, but they do have primary alcohols, so they will definitely respond to this test. Okay. Now, this isn't really useful in the sense of figuring out whether something's a ketose or aldose, but it is useful in structural things, and we'll see that in the exam. Actually, there's questions, surrounding the use of these tests to figure out the structure. Okay, cool. All right. Sorry, let me just quickly check. I don't think I missed any oxidation tests. Oh, I did miss one actually, I think, but technically it's. Okay, cool. All right, cool. So all that's left now is the oxidative cleavage. And so this is just the complete digestion of a sugar. And there's really only 2 things you just need to understand what makes what, and then we'll move on. Okay. But every sugar has the potential of having 3 parts to it, right? It has carbonyl, primary alcohol, secondary alcohol. The HiO4 test digests these sugars and produces the following groups based on the functionality. Okay, it can potentially form a formic acid, a formaldehyde, or a CO2. Okay, formic acids are made by the secondary alcohols. It's also made by the aldehydes. Okay. Formaldehyde is made by the primary alcohols, and the CO2 is just made by a ketose. Okay. So usually with these questions, you'll see them ask, what is the relative proportion or relative ratio of every group and what is formed? So in this case, we make 1 times formic acid. Great. Actually 2 times, right? Times 2. And then we'd make a formaldehyde, right? Times 1. We'd make 1 times CO2, 1 times formic acid, and then these two would make formaldehyde, right? 2 times, right? Mechanistically, the way that this works is if I have a vicinaldiol, right, and I have the IO4, HIO4, so something like this. I don't remember the exact arrows, so I'm just gonna kind of speed through this, but you'll get a complexation. Yeah. And just get a oh, like that, something like that. Where the bonds just kind of break to form these here. Okay. And so this will just keep going on as long as you have vicinal alcohols. For the ketone and the aldehyde, so aldehyde will first turn into vicinaldiol, or sorry, into a geminaldiol via the water in solution, and then you'll do the system. So you can actually figure out why this makes the formic acid, right? Because when we get to here, right, that, right, what you'll get is the formic acid. You'll see the OH there, and then, I mean, in this case, CH2OH, right, will make the formaldehyde. Okay, cool. That's all I'm going to talk about for that, just because we're way over time now. Okay, cool. All right. So all that's left now are the reductions, so aldehdols. Very, very simple. If you have an aldehyde, right, NaBH4, CH2OH. Okay, very simple. Just watch out for the ketoses. As a ketose, don't know which way the alcohol is going to face, so you can use a squiggly line, but you get away with it. Right, the squiggly line just means epimers. Okay, so if you want to use a squiggly line, I would just advise throw epimers on the side of it, just so your TA can talk you. That's what this means, is that you're forming epimers. Okay, cool. All right. I'm not going to go over lysosome. It's pretty simple. We'll talk about it during the exam anyways. Cool. All right. Let me just see what else is there. Yeah, we'll see lysosomes. Cool. All right. So all that's left now, again, I just want to, well, actually, I guess there's no time to this, but I wanted to go over why these tests were important. There was actually a synthesis that I wanted to talk about that Emil Fischer did. I wanted to write this as one of the midterm 3 syntheses problems, but there was just a better one that I wanted to use. And I thought this might be a little too hard. But Emil Fischer, right? One of the things that he did, one of the things that he had to do, which to kind of highlight his genius, is he had to turn D-glucose into its flipped version. And so what I mean by that is he had to turn it into this. Sorry, what? Oh, my bad. I blanked on those two. Into this, which if you turn this around, yeah, if you were to rotate this like 180 degrees would be, I believe, L-glucose. Let's be glucose. Okay, so this is glucose. It says gulose. Okay, it doesn't have the C in it. Okay, and so gulose is not naturally available. He had to make it on his own. So he had to synthesize this, or he was offered the challenge of turning, a CH2OH into CHO and a CHO into CH2OH. Okay, and so you can actually do this transformation using the chemistry that we've just talked about, right? Using these tests. kind of a strategy you might want to think about is, if I think about what I'm doing here, I'm essentially reducing the aldehyde. I'm doing a reduction here, and I'm oxidizing this here. So you can imagine, right? We want to do some kind of like a primary alcohol that's like an HNO3 essentially. Here we want to do like an NAPH4 type thing. Okay, cool. Now, here's kind of the issue with this, right? Is that HNO3 is such a powerful oxidizer. So you can't just straight up throw HNO3 and expect everything to go perfectly, right? We're going to form an aldehydic acid if we do that. So to begin the synthesis, right, Fischer had to protect the the aldehyde. And so you can imagine to do this, right, at least when we think of carbonyl protection, we think of acetals. But remember, right, this is a sugar. So the sugar is littered with alcohols. So in fact, Fischer just used the natural, components of a sugar to kind of help them out. What he did was an acetal protection with the sugar itself to form the glucoside, or the glycoside, sorry, so that he could protect the aldehyde as an acetal, but of its own natural form, right? The sugar already naturally maintains being a ring, so he just kind of put a lock on it with the acetal. Okay? So he's able to now oxidize that primary alcohol without worrying about oxidizing the aldehyde. Okay? Once having done that, you can just hydrolyze this, right? Just get rid of it and turn it back into this. So now he's kind of achieved the oxidation that he needs, right? So he's overshot it, but he's gotten to that oxidation level, to a higher oxidation level that he needs, okay? Next thing you do is just kind of, now reduce the aldehyde without much worry. Form the CH2OH here. Now, a couple of you hooligans might even say, why didn't you just do that in the beginning, right? Why didn't you just turn to CH2OH instantly? What was the whole point of protecting the aldehyde? Well, you silly goose, that's a CH2OH, right? If you reduce it instantly into CH2OH, then HNO3 would have oxidized both of them. We would have been back to the same aldehydic acid issue. So pay attention, right? It's the whole point of listening to me here. Cool. Anyways, just having some fun. But now we have the appropriate oxidation state of the alcohol. Now we need to kind of, slowly reduce this acid down, right? Well, if I want to turn my carboxylic acid into an aldehyde, right? Remember, this is just a chapter 19 ordeal, right? How do we turn acyl derivatives into an aldehyde? Well, usually you don't go through that acid, right? You turn the acid into a derivative. And again, if I kind of look at the natural sugar, I have a carboxylic acid, a bunch of alcohols. You guessed it, right? He can turn it into that lactone we talked about earlier, right? And then use like a Dibble reduction, for example. I don't remember the exact one they use, but for you guys, Dibble would be the appropriate reagent, right? And that Dibble reduction gives us the aldehyde. Oops, sorry. Gives us the aldehyde from that ester. And now our flipped sugar, right? Now you want it to. Cool. So just to show you that these tests are not just tests, they can also be used to our advantage to make new sugars, and also just offer you guys a really interesting sugar type synthesis, right? That's a bit difficult, but I think now that we talked about it, it makes a little more sense. Cool. Hopefully you guys found that entertaining like I did. All right, so to finish off the class, or sorry, not the class I wish, right? But to finish off the chapter, all that's left are now the sugar reactions as rings. So remember, a sugar, generally speaking, is 99% of the time in its ring form, right? It spends 99% of its time here. So, we should understand the reactions that we can do in this form here, okay? Now, this here is glucose, which generally spends most of its time in the beta enantiomer. So we'll draw that out. But this beta enantiomer is a little interesting, right? If we were to introduce to it let's say acetic anhydride and pyridine, right? We can acylate all of these positions here to form glucose pentaacetate. Okay. So what we'll get is this here. So basic conditions, because this is a base essentially, right? Basic conditions call for complete non-selective, right, acylation. And you can imagine if you did like an alkylation, same exact ordeal, right? If I did CH3I, same exact thing. You would get complete methylation, absolutely no discrimination whatsoever. Every single alcohol methylates. Actually, in this case, the beta anomer, so technically the anomer should not change. So we retain anomer. That's the general rule of thumb. But in this case, actually the anomer will not be retained because of that soak forth, right? That very weird anomeric effect we talked about in the lab. If I had more time, I'd talk about this, but I don't. So I will leave it be. But generally speaking, you have a complete non-selective acylation and you retain your anomer. Okay. So what happens when we use acid, right? Well, it turns out if we use acid, remember when you're an H plus, think C plus. When you consider all these alcohols here and who would make the most stable carbocation intermediate, it is always the anomeric OH. And the reason for that is because the anomeric OH forms a cation that's able to resonate. The rest cannot do so. Okay. And so this resonating cation can be attacked by a nucleophile on either the top or the bottom. But what results is a mixture of isomers. Okay. So now we have selective anomeric reaction. So selected to the anomeric with mix of anomers. So acid and base are completely opposite, right? In base, we have a completely non-selective acylation or alkylation, and you retain the anomer usually, 99% of the time you will, okay, except for this one here. Okay. In acid, though, you get a selective anomeric transformation of your nucleophile, and you get both anomers, okay? And nucleophile can be a lot of things, right? It can be an alcohol. It can be, and usually sometimes you also see amines. Okay. I mean, think about it. Sugars have all these alcohols. It can literally be a sugar. So another sugar can be your nucleophile. Okay. So to put all these concepts together, I can start with beta glucose. Right. Do a complete methylation. And if I do a hydrolysis, right, at a low temperature, weaker acid, right, you will only get anomeric hydrolysis, and we will get both anomers as a result. Okay, cool. All right, so keep that in mind. Base, complete, retain of anomer, acid, anomeric. So acid, anomeric, right? They both start with the same letter. Okay? And we get a mix of atomers. And sugars can also, get involved in the mix. Cool. All right. Just for sake of time, just going to move on, trying to finish this up in like 10 minutes. Okay, cool. So all that's left now are the Cyanide Fisher and rough degradation. So how to build or break a sugar. Building, very simple. Take an aldose, and you can do KCN, HCl, which all you do here is you replace CHO with a squiggly OH, H, and CN. So we form epimers instantly. Okay. And then you do a two-step sort of reduction in hydrolysis. You H2PD over barium sulfate. This is called the Rosamond reduction, I believe. Which will initially give us the imine, which you can then hydrolyze fairly easily into the aldehyde. Okay, cool. So aldoses increase linearly very easily. It's a matter of counting, right? How do I know this reaction occurred? 3 to 4 carbons. Very, very simple. Okay. If I wanted to use a ketose, I can. The reaction just looks, or the product just looks a little different. What is it? What does it look like now? You just replace the ketose swiggly with an OH and a CHO. Okay. So you can kind of see here on a ketose, it doesn't really expand linearly like a natural sugar would. It kind of expands like to the side, which is a little weird. Sometimes you'll see this rotated though. This, which is kind of, I mean, this is fine. But again, like sugar didn't like naturally grow. It kind of grew to the side. Cool. So Cyanide Fisher, add one, pretty simple. Okay, cool. Rough degradation is the breaking down of sugars, which is fairly simple. Okay. This only works for aldoses because the first step is Br2H2O. So we get the oxidation at the top there. And then some Fe3 plus Lewis acid and peroxide will do decarboxylation. So we'll lose that carboxylic acid radically, usually. And then this radical can resolve into the aldehyde. Okay. So you lose a carbon in this case. Okay. Very easy way to recognize this. Or to solve this. I have any number of centers here. At least this is what I like to do. I just get rid of the top 2 centers and I just copy everything else. Just put a CHO in place of everything I erased. And there you go. Cool. Just I'll just different stuff here. And this will stay the same. Cool. Well, that's it. Those are both chapters kind of sped run within, looks like 2 hours. So, or like an hour and a half. I think it was like an hour and a half. So that was a little over my goal, but whatever. Can't really do much about that now. Yeah. Cool. All right. So that's our review. If there's, I'm kind of like scrolling through the textbook right now. See if I probably missed 1 or 2 things, but I mean, what can we really do, right? vocab wise, cyclizing wise, I did include a video in the Discord for any cyclization worries. So by all means, you're welcome to go ahead and look on there. If you need help with cyclizing, I have a method that I like to do. But there is a question on here that I think requires cyclizing anyway, so we'll see it anyways. Okay, cool. All right. So let's just get into the midterms now. And we'll have to go through this very quickly. I don't want to take more than an hour on both of them. So I'm gonna have to go fast. Probably gonna have to skip like some mechanism stuff and possibly some of the stuff here. But anyways, cool. Let's get into it. All right. So always the first midterm is much more response. Just what you learn immediately in class, just kind of write it down. So you have an ester. Side matches the ester. So Claisen condensation, just make sure 2 protons there. So this will work. Remember, this is an acylating reaction. The essence of it is, so all we're doing is we're adding all this here, right? So just that. Cool. That's all we got to do there. Ways you can change this up is to add in some of those quirky, partners I talked about. So for example, this guy here, nothing to be afraid of, right? It's just an acylating agent. Just be aware of its existence, right? Stuff like that. Cool. All right. Moving on to B, right? We have ketose, and NABH4 is just going to reduce that. We just don't know where. So I would just put squiggly line as such. And then just to be safe, throw in that epimer on the side. Just like that. Cool. All right. Looking at C, we have a sugar. Again, with the sugar reactions, just want to go back up here and talk about this. You can do that thing where we do 3 other reactions on it. It's much like midterm 1 we can do that. Like maybe I do Killiani-Fischer instead. On a ketose, remember that's just OHCHO. Or I'll do it this way. Doesn't matter which way you add it. Right. Right, that's Killiani-Fischer. Rough degradation, would I work on this? HNO3 would just turn into COH. So by all means, right, turn these 10 problems into 30 by doing multiple things on them. All right, moving on to C, we have a sequence of NaOH into H+. So you can imagine, first step, we'll do that non-selective methylation across all of these. And then that second acid step will only hydrolyze that anomeric position. So this is actually not a very clever question. It's exactly a rewrite of what we just talked about. Oh my God. Faster, I want to get things done, the worse my handwriting is. Okay, cool. Now again, a lot of things you could have done here. You could have done an acylation. You could have done, one thing that some professors like to do is they will draw something in a ring form, but they'll do like an oxidative test on it. For example, Br2H2O right here. That just means you just got to open this up, which can be kind of a pain. But to kind of walk you through very quickly how I would do it is the first thing I could do is just count all the carbons. 1, 2, 3, 4, 5, 6. So 6 carbons. 1, 2, 3, 4, 5, and then 6. Because there's an H here on the anomeric, this is an aldose. And at the bottom, we'll have a CH2OH. Okay. Now it's just a matter of your ups and downs. Okay. So this here is down, so it's on the right. This here is up, so it's on the left. Right? Down, so it's on the right. Okay. And then when we get to here, right, this here is our cyclizing O. Because the CH2OH is up, this must have been down, so it'll be on the right. Okay. Cool. All right, so look at this, and then you can do like Br2H2O if you wanted to on this. So very likely this could be asked. Just maybe it is. Just wanted to bring it up just in case. Cool. All right. Moving on to D, we have an interesting diketo, like a bis keto ester. Or I don't know what you would call this, to be honest, but it's like 2 of them. And we have base, and we have this interesting dibromide. So I'll kind of line things up here. But you can imagine, right? Remember, when we think about where the base is going to protonate, be either here or here. And then we have a dibromide species. So, wonder what's going on here, right? You can imagine, boom, boom, plug those in together. What we end up with is this here. Okay. And so that H3O plus in heat step, you can imagine it's just decarboxylating off those esters just like that. Okay. So this is our ketone product here. Now, a lot of people that are going to do this stepwise will do this, right? They'll form the cyanide here, get rid of this, and they'll ask the question of, okay, well, now I'm confused because why can't, sorry. Right? Why can't the anion form here again, and then just attack like that, and then form a triangle, right? Triangles are kinetically the fastest, and that's totally possible. So why can't this happen, right? Why is it that we form the pentagon instead? Well, it is very true that we could form the triangle. In fact, actually, forming, a shape, a spiral shape like that in between is very common. You'll see this with 5 members especially. You can do this. But what might be the driving force in making the pentagon here is the fact that when the base, right, this minus here, goes to pick up a proton, right, both these protons are equally acidic. Maybe this one's a little less acidic because we have that basic carbon group there, or like we have an extra carbon group there. But in terms of pKa, these are all about the same. So it's a matter of chance. There's twice as many protons here than here, just 2 times more likely to take off this proton that is take off this one. So it's just a matter of kinetics, just a matter of chance. It's very likely that this is possible. It's also very likely that we might even form a little bit of this here, but I'm willing to put my money on the fact that we will get the pentagon more often than we'll get the triangle. Okay, cool. All right. Moving on. We have an ester, 2 protons. We see the base with some kind of quicklime. We see that carbonate, so it's just a acylation with an ester. Okay, to make that malonate ester. Okay, so nothing too crazy there. Okay. And then if we wanted to, we could have added stuff here and then decarboxylated. But just something we could have done up. We just didn't do it this time. Cool. All right. Moving on. Hey, look at that. We have a sugar in its cyclic form, its hemiacetal form, and we're doing an oxidation test. So we've got to go ahead and open this up. So again, 1, 2, 3, 4, 5. It's to be a 5-membered. I'll just look here right now and see that this is an H. So this is an aldose. So 1, 2, 3, 4. Sorry, 2, 3, 4. And then we'll do 5 down here. So it's an ups and down game, right? That's down on the right. This is up on the left. And this is up also on the left. Okay. So we've got our sugar now filled in. Now we can just do our oxidation test, right? Which is just COH. Like that. We then have a heat step, which remember, all that really is a lactonization, usually a 5-membered ring lactonization. So this is 2, 3, 4, and 5. Right? Lactonization is just going to occur like that. So we'll make a 5-membered ring. Don't worry about stereochemistry too much. We're on that 5th carbon. We will have a CH2OH coming off of. Cool. So if we have a hemiacetal center, we can easily open it up and we can do our oxidation test. Something I didn't really talk about that I should have is that if we have an acetal center, right, so like a CH3 here, this is no longer hemiacetal, right? We no longer have access to that equilibration. So in fact, now we no longer have a reducing sugar, right? This sugar should not respond to any oxidation tests. So, because we don't have that open chain anymore. Okay, so boohoo, no longer available to us, this chain here. So something like an acetal shouldn't respond to Br2H2O, but there is 2 oxidative tests that kind of get through this. One of them is HNO3. So HNO3 actually gets through this because it can oxidize this guy here. So you can imagine it will form a COH. Okay. So that one gets through. The other one that kind of gets through is the HIO4 test, because periodic acid, remember, it just digests acetyl alcohols. So it's easier to think about it in the linear, but I mean, these are acetyl alcohols. So this will cut between here and it will cut in between here. And you can imagine, right, it will not cut between here. Could also actually even cut in between here, right? Could it? No, actually, no, it cannot. Sorry, that's not vicinal. I was thinking about these two here. So it will cut here and here because those are all 1,2 diols, right? You can see this guy kind of gets liberated out. So that guy will come out as a formic acid, right? And then we'll have a chain that's oxidized. Right, so if I kind of draw the shape of this, right, we'll have a chain that's oxidized like this, and then oxidized like that. And then that was the center carbon. It kind of got oxidized out as formic acid, or formaldehyde, sorry. Okay, so very specific example, one that you might want to write down or, just think about to understand. So there are technically 2 oxidation tests that can get through the acetal. Okay. Cool. All right. G, we have diethyene and butyl protonate here, and then we'll go ahead and attack there. So we will get this here. Oops, sorry, like that. Remember, we can either do HgCl2, which will turn this into this, or we can do H2PD, so just hydrogenate that center, right? Just keep in mind that H2 rainy, sorry, not PD rainy, will also hit that alkene, right? So that's the one that people always forget about, hit that alkene there. So, look out for that. Yeah. Cool. All right. We have an aldose here. We have the Giuliani-Fisher sequence. So very, very easily just mock up this here. I want to add squiggly line, right? Epimers here, and then put CHO, OH, and then H. Okay, cool. Pretty simple. HH. All right. Rough degradation, right? Just get rid of those. And make L-glyceraldehyde here. Cool. I apologize if I'm rushing a little bit. You can imagine it's getting pretty late. It's like, around 3:30. Do you want to finish this by 4 so I can just go to sleep? Cool. All right. Although it's like this is my fault for doing this so late. We have a ketone, we have an ester, or a formate ester. So we're doing, again, another Clayson type acylation. Remember, our nucleophile needs to have at least 2 alpha hydrogens. So despite the fact that there are 2 positions here, it's very easy to know which one's going to do the attack. It's going to be this one here. So that's going to attack there. And again, we're just acylating, or in this case, formulating. So we're using the formate ester. So we will get an aldehyde at this position. Cool. Last but not least, we have, HNO3. Just talked about this, right? This is an acetal. So technically, oxidation tests would be impossible, right? So if this were, for example, this sugar here, if it were this sugar here, then this would be NR, but we don't really ask NR questions here. So there is a response. The response is on that primary alcohol. To form the COH. Sorry. There we go. COH. I hope you guys don't get something crazy like this one. This is hard to draw just because of all the bonds that are conflicting. Okay. Cool. Again, if I did like an HiO4 here, we can cut between all the vicinal diols. So there and there. And so what we'll get is a formic acid. Oh, sorry. Formic acid, not formaldehyde. What am I saying? I think I drew a formaldehyde on the previous one, so I apologize. I already know someone's going to ask. So just late. I apologize. And then the rest of this. So that'll oxidize. that will oxidize, but this will stay the same, and then this here will stay the same. I know it's a rough drawing, I apologize. Just, it's not much I can do here. I guess I could do this. Draw this longer. Cool. All right. Just moving on. All right. This mechanism is in your notes, so just practice it. Not much I'm going to say there. But this one here is an interesting one. We have a base, we have a ketoester that somehow magically transforms into another ketoester. So what's going on here? My hint to you, just to think about it right now, is that this here is a like kind of tertiary quaternary center. Right? We have two groups there, neither of which are H. So maybe think about what I talked about, what happens when you don't have hydrogen there. Okay. If you don't want to think any more harder, this is a retroclason, right? Because remember, the base likes to deprotonate this position here. And if it can't, the only thing it can do then is attack the ketone in a retro fashion. So we're inducing a retroclason, which is the exact opposite of a normal clason, okay, where base adds back in, minus comes down, and instead of kicking off the oxygen, right, kicks off the acyl group. So undoes the acyl attack such that we form or reform the acyl anion that attacked. And again, if we look at that acyl anion, if I kind of unravel this, 1, 2, 5, 6, 2, 4, 6, right? It's on a center that does not have 2 alpha hydrogens. So, right, that center was never made to do clason, right? So wasn't the point of it to be there. So what we can do here then is have an acid-base transfer onto the center that can do this. Reattack in, this time getting this isomer here. Right, kick this guy off. Okay, and then OME, remove that proton, and we get our beta keto ester that we see in the product. We'll get the deprotonated version. Okay, this will just go ahead and hunt a proton, right? And we'll get to here. So this is the retroclason, which you guys are responsible for. You should understand how this works. So key thing to tip this off was that, you know, quaternary center, the base can't deprotonate. So if it can't deprotonate, what's it going to do? It's going to attack, reverse the mechanism. Very common trick used in synthesis all the time to induce these rearrangements. Cool. All right. Moving on to synthesis. The syntheses I had to get kind of creative with because there's only so many ways you can do these. The sugars. So I'll kind of just teach you the tips and tricks I see. So 2 things that I noticed in sugar, right? One is that this is epimers. So we don't know which center is epimerized, but we do know that one of them is. So we know that whatever reaction took place kind of scrambled the center. We don't know whether it is left or right. The other thing I notice is that we have these COHs. So we can get rid of that. That's just HNO3. So I can get back to this here. And so now what I want to think about is where in the world did this sugar go, right? Because I went from an aldose to a ketose, which almost seems like it's impossible. How in the world did this even happen? But I've got to make a guess, right? Because I need to know how to proceed, what I need to do next. So the guess that I would make here is that, I mean, we have a carbonyl here and we have one here, right? Aldose to ketose. If I had to guess where that carbonyl went, I'm going to assume that they're the same, right? Because again, I mean, they're technically the same functionality. They are both carbonyls. One just has an R group on it. So if I assume that, the ketose carbonyl used to be the aldose carbonyl, what I notice is that this component here is 3 carbons long. This here is 4. So you can imagine we went through some kind of rough degradation. Okay, so you can go ahead and do a rough degradation here. Okay. And then what we can do is the Fe3 plus H2O2, and that will give us diglyceraldehyde. Okay. And so now we can see that we have our 3 carbon piece here and here. So all we have to do now is add on another 3 carbon piece to our diglyceraldehyde. And so maybe we're thinking, okay, so we gotta essentially couple 2 pieces together. And maybe what I notice is, well, if this is my diglyceraldehyde, that could have been this guy here. What I'm adding to it is this triol. Well, wait a minute. What I'm forming, that new bond here that I'm forming, is an alpha hydroxy ketone, which, if we think about it, we can do with thiamine or dithiane. So this is going to be a thiamine-dithiane type coupling. Now, the kind of clever thing here, is that this here is another 3 carbon unit, which you can assume, oh, that's basically diglyceraldehyde. This is a coupling of the same sugar. So what I'm doing is I'm taking 2 sugars and I'm coupling them, 2 aldehydes, and I'm coupling them, right? When I couple the same aldehydes, that means I'm using thiamine. So, one thing you might want to do instinctively here is do this. At your guys' level, this is totally fine to assume that you can go ahead and do this. So thiamine KOH to get us here. But there's actually a tricky thing here. In fact, sugars, when they do these coupling reactions, act a little differently because of these adjacent alcohols. Mechanistically, they can do what we call acyl transferring. Actually, that's what happens in the body, is the body uses thiamines to transfer the acyl groups of sugars around. So what you should really do first is an acetone protection. Okay, where's the vicinaldiol? It is right here. So we can protect those guys. So we can protect those like that, just so that the alcohol doesn't do anything annoying. And then we do our thiamine protection, our thiamine coupling. So I'm just gonna put thia here. And what we'll get will be our coupling as such. Oops, sorry. And then we can just do like a hydrolysis to get to the product. Oh, sorry, hydrolysis to get to here, and then do the HO3 to the product. So you can do like a repeat step here. I suppose, no, actually, no. I don't think you'll have any problem with any polymerization or anything. Cool. All right. So kind of a tricky problem, but again, just kind of going through our concepts, right? We saw the double oxidation, so we knew it was HNO3, right? Again, using the idea that, hey, I think that my carbonyls are the same, so I'm going to go with that and try to figure out what I did here, which was, okay, if this is the same as this, right? I have a 3 carbon fragment, right? That went from 4 to 3, okay? And so essentially, I'm doing a rough degradation, okay? And then from there, right, I am then doing a thymine coupling because I'm adding 3 together, right? Doing a dimerization of my sugar. I guess one way that you kind of recognize that you want to use a thymine here is the fact that we're going from an aldose to a ketose, right? Not very many ways you can do that. In this class, this is really the only way you can do it, is to use a thiamine or a dithione. I guess you could have also used dithione here, but the only issue that I have with dithione is that dithione is so basic compared to an alcohol. I don't know if it would survive the hydroxides. So cool. So cool little reaction there. And just kind of exposing to you what you can do with sugars, right? I mean, hopefully you guys also learn to, see the complexity in sugars, especially with that when we were with Emil Fischer's synthesis, right? That's a pretty gnarly synthesis. Cool. All right. So that's a hard one. Bit of an easier one though is this guy here, okay, which is the diketone from the ester. So diketone, ester, you can kind of see where this is going. This is going to be some kind of Clayson. So if you wanted to, you could almost even start with the Clayson here. Although I guess you don't know if this is self-Clayson just quite yet. So maybe we don't. But remember with Clayson products, the dicarbonyl products, it's very easy to break down when they're beta keto esters. When they're diketones, it's a bit trickier, but you kind of have to take like a risk. You have to take like a leap of faith. So because you don't know which one was the original ester. So I'm going to go ahead and just label alpha beta like this and just move forward with this cut here. And let's see if it works out for me. Okay. If it doesn't, it's okay. We'll just go back and use the other fragment. Okay. But again, on the beta, we want to add an OR group. So I'm thinking that these two coupled together right? R minus ROH in heat. Okay, cool. But now I have a ketone that I can work with. And again, remember, in the context of this chapter, if I have a ketone, right, I know that there might have been an ester next to it, right? The whole point of the beta keto ester. So possibly some kind of decarboxylative sequence. Question is, which alpha carbon do I want to put it on? Think about this for a second, right? Which position do I gain some kind of advantage by having an ester on? Is it here or here? Rule of thumb, the branch center is where you want to put it, right? By putting it here, right, I'm allowing myself to add in this alpha branching. Okay, now this alpha branching is a little bit interesting, right? It's a ring, but it's still branching. So I'm going to go ahead and say that, okay, that there, right, that branching there, right, it's only being able to add it on with the assistance of the ester. Okay, so now when I think about cutting this apart, right, they're just chained together, those two pieces there. So it's not anything crazy. It's just like what we saw before. It's just going to be a dibromide. So first step will just be base. And second will just be this dibromide species. Okay, that adds on here. Again, this is different from the one that we did before in the predicted products because that one had another beta keto ester that formed a better not spiro type ring, right? But without that being there, we have to form the spiro and it's totally fine. It's totally possible. It's not impossible to have that there. Okay, cool. So this is our dibromide species, which leads us back to this beta keto ester, which again, all I have to do here is alpha beta from the ester cut here, RO minus ROH delta. And what I get is a beta fragment and an alpha fragment, beta fragment add OR. And what do you know it? This is just the original product, right? If this is just methyl group, just being added together, right? It's a self-Clayson. Cool. All right, so that's our two syntheses, and hopefully you guys can see, mainly the concepts of the second one. The first one was a little tricky. It's a bit more of I think that might have been more of an ego thing for me to do, but still cool, I think cool nonetheless, right? Hopefully you guys can appreciate that one. Cool, all right. Moving on. So this is what I was talking about, these new types of problems where you can have, you kind of are in Emil Fischer's shoes and you're kind of figuring out which sugars are which just by doing these kind of tests on them. So you're given a piece of information, the aldopenta. So if you wanted to, you could kind of draw a structure here. So 1, 2, 3, 4, and then 5. Okay. 1, 2, 3, 4, 5. Yeah. Yeah. So you kind of get here, but we don't really know where the OHs are. So let's just kind of walk through the transformations just so we have something down. BR2 will do this. And then, right, you will get this from the reduction. And then we'll end up with this. Okay, cool. So at the very least, we know that this is going on because it's a sugar. We just don't know where the OHs are in this. So it's dependent on our optical rotation to kind of tell us, right, what it is that where our OHs are, right? Zero optical rotation means achiral, right? Non-zero means that it's chiral. Okay. Usually with achiral molecules are meso. So in the case of this one, that would be when both OHs are the same way, because you can see the mirror plane down the middle, just like that. Okay. So this is the final structure. And we know that our OHs on those bottom two centers must be facing to the right, because we had a zero optical rotation. If there was a non-zero optical rotation, the OH would have been on the left side on either one of these. So it would not have been clear which one exactly we had, but it would have been one of them, right? But in this case, we get zero, so it's look like this, right? From here, though, the question becomes, how do we know whether the OH is on this side here or this side here? Okay. Now, from this structure here, it's not very possible to tell just because it will always be non-zero, whether it's here or here, because there's no symmetric group there. But some information given was that if you take the starting material and you treat it with HNO3 such that it makes the COHs on the top and the bottom, just like here, it is non-zero. So it is still chiral, right? If the OH at that top center were on the right side, right, putting COH here and here would have been an achiral compound because you can see the mirror plane down the middle, right? The fact that it's non-zero means that it must be chiral, which means that the H must be on the left side. Cool. So there you have it. That's a way you can kind of walk through this with just 3 reactions to figure out the structure of a sugar thing there, right? I think there's another problem I wrote with this, so the other midterm will also have the opportunity to practice that. Cool. All right. General knowledge. This is vocab terms. Blank oxidized C1, C2. So this is phenylhydrazine. This is an Osazon reaction. Only thing to understand about that, doesn't matter what kind of sugar this is, but these reactions always turn the C1, C2 position into the hydrazines. So one thing that's of particular importance of this is that certain sugars that are not identical C1, C2, but are identical below that will give the same osazone. So for example, this is glucose, right? Glucose gives the same osazone as mannose here. So these give the exact same osazone. Okay. Why is that? Because when I kind of block out C1, C2 here, because these become identical after the osazone reaction, you can see these are the same, right? Left, right, right, left, right, right. Okay. So that's the osazone, the cool thing about that. Okay, cool. All right. Moving on. Blank is a major energy source. So this is glycogen. And I mean, you just need to know this glycogen, I believe, is alpha 1,4 subunits, I believe, glycosidic subunits. I believe so. I don't remember. So just check on that. I'm pretty sure it's alpha 1,4. Cool. All right. All I did was look at your study guide, looked at the terms, made sentences, so you guys can do that too. All right. Draw the pyranose of alpha D ultrose, which is the C3 epimer of glucose. Cool. So what that means, 1, 2, 3, right? That's going to be this guy here. Okay. So the sugar with all 4 of these OHs on the right side. Since we want the pyranose, we want the 6-membered ring. So 2, 3, 4, 5, 6. This is 1, cyclizing there. So we will form this 6-membered ring here. It's the alpha D sugar. So that means that on the alpha position, we want it to be down like that. And we'll have an H here, right? If they were a ketose, we just have a CH2OH here. So ketose versus aldose in ring form, just look for that H versus CH2OH. Okay, but we have an H here. Now, for me, it's just a matter of ups and downs. These are all down because OH is on the right side. So down here, down here, down here. Okay. And then when we get to that 6th carbon, right? Or that 6th carbon, remember that 6th carbon is acyclizing. So this is actually O1 right here, right? That's that O we have is pointing down. So it wouldn't make sense to put an OH pointing down like that. What we want to do is put everything below that on this carbon. So below carbon 6 is CH2OH. So that's going to go here. Where does it go in space? Well, this OH had to be down, and this guy must have been up. Okay? So that guy will be up there like that. Okay? And there you have it. That's the pureness of alpha D-aldose. Cool. All right. Sake of time, we gotta get through it. I want to finish the next midterm in like 20 minutes. Just probably impossible, but we'll see. Cool. All right, last problem. We're not going to do nomenclature. Which of the following is most prone to decarboxylation? In order for us to decarboxylate, right, you need to form a carboxylic acid. So ketones are kind of not going to work out here. We have ester here and ester here. And the easiest way to think about this is to draw the anion of this bond when the ester leaves and look at its conjugation, right? This, you could argue conjugation is of the ring, but I mean, benzylic conjugation is not the best. I mean, it would only be pKa of like, I mean, it's like a P of like 40, right? And there isn't like some EWG on the ring. So I'm not totally convinced of this, but if I take this system and draw the anion here, right, this is going to resonate into the carbonyl. So if I get rid of this, it's going to resonate to the carbonyl. So very likely decarboxylate. Yeah. Again, this is the poster child because that anion there is delocalized directly into that carbonyl, but it's good to understand again generally what decarboxylation means. Cool. All right. So that was the first midterm. Hopefully that was fairly straightforward. Again, you can take these multiple choice and do so many things with them. For example, I mean, what you could do is you can turn some of these into ketoses, right? Like turn this into a ketose if you wanted to. You could do that. And do the problem where you open it up and all that nonsense. You know, do other sugar reactions, blah, 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 whatever you want to do. Cool. All right. So let's just get through this here. All right. First reaction, we have Br2 into Fe3 plus. So rough degradation. Boom. That's it. In 2 seconds, I did this problem. I expect you guys on the exam do it in 1. Cool. Imagine if we did Kiliani-Fisher or Br2H2O, right? What that would look like. Cool. We have a ketone and an ester. So this is going to be some kind of Claisen condensation because we have that MEO minus. We can't really match the base to this this ester here, but we can pray that it will not do a substitution. So let's pray, right, to hope that it doesn't do that. But you can imagine minus here will attack there. So why attack here than here? 1, 2, 3, 4, 5 versus 1, 2, 3. I guess 3 could attack, but 5 is the better ring, right? So we're going to go ahead and assume that that's what's going to happen. So 1, 2, 3, 4, and 5. Okay. 1, 2, 3, 4, and 5. 1 attacks 2, so 2 will be where we form our keto group. Right? This is going to leave, so 3 is going to have the alcohol. Should be 2 carbons of alcohol like that. 4 has nothing. 5 has the ketone that attacks. So we end up forming this. The more correct version of this is the lactol. It's okay if you didn't have that. Technically, this is just 118B material, where the lactol is a bit more stable. Okay. Now, it's totally possible that we do get uh, esterification first, but that doesn't really change anything. This will just still go ahead and do that. It's just much more clear now that it's doing that. So it doesn't matter whether this goes in a text. Cool. All right. HIO4, complete digestion. Again, you could open this up if you wanted to, but you don't, it doesn't really matter where your OHs go. You just need to know how many things are there. So I would just count 1, 2, 3, 4, 5, 6. Right? Note that this is a ketose. So this here. So 1, 2, 3, 4, 5, and then 6. Know the OHs wherever, although it's good practice to know where they go. So we should just practice this, right? This is OHs up, so it'll be on the left. So OHs down, so it'll be on the right. And then this one is going down, so it'll be on the right. So it's good practice, but you don't need to know this because, again, HI4 is just cutting here, 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 and here. And it's just a matter of what you have. So we have secondary alcohols, which are going to form formic acid. And it's going to form 1, 2, 3 of them. Okay. We have 2 primary alcohols, so those will form formic acid. Okay. And then we have ketose, which will form CO2, just one of them. Okay. So 1 by 2 by 3, or 3 by 2 by 1. Pretty cool. Okay. All right. Again, you can imagine other reactions you could do on this if you wanted to. Like acetal protection. Oh, I realized I didn't cover that, but it's in one of these questions. So cool. All right. Moving on. D is dinitrile, and base. Remember, this proton here is the same as an ester, so don't be afraid of it. It's going to fall up just like an ester does. This will just attack there. So what we get is this here, and then hydrolysis will turn both of these into acids, which, whoa, look at that, right? This will just decarboxylate. So just an alternative method that you could use if you wanted to. Cool. All right, moving on. E is just in water, so it's just a standing water cyclization. Usually you can make 5 or 6 from this. A good question will not ask you to do more than 2. Or it will just ask you to do, like a 5-member. So I engineered this so that 2, 3, 4, 5. 5 was the only one possible. Just so you don't have to draw so many things. We can draw a 5-membered ring here. Okay. And so again, we don't know the enantiomer configuration, but it'll be OH, and then we'll have CH2OH here because it's a ketose. Okay. But again, on 3, we have an OH on the left, so it will be up. Okay. We have an OH that's to the right, so it's to be down. And then 5 is a CH2, so H is like that. So we can just leave it empty. Cool. All right. Moving on. And just very quickly, but this minus, I mean, there's no protons there, right? I mean, let's go this first, right? The base matches the ester. We have an ester with 2 protons, 2 esters. It's just gonna go like that, right? We'll get rid of this. Kind of see how it's gonna form the product. It's a 5-membered ring. Okay, cool. All right. This is Kiliani-Fisher. Just to very quickly draw the product. Squiggly, OH, CHO, OH. There you go. Not too crazy, not too shabby. Cool. All right. We have a dialdehyde. The aldehydes are identical. We have thiamine. Should not surprise you that we're just coupling right there. So we are essentially doing this here. Right? Again, intramolecular is fine as long as they're the same or it's a keto ester, because the aldehyde will activate and attack the ketone. Oh, sorry, not keto ester, keto aldehyde. That's what I meant to say. Brain fart there. Cool. We have again another thioacetal. Form the H there, take it off. Sorry, have the H there, take it off. Aldehyde versus ester, right? We're going to attack for sure the aldehyde. No doubt about it. So what we're going to get is going to be this here, like that. HACl2 tells us that the thioacetal turns back into a carbonyl. Cool. All right. Again, if it were H2 rainy, it would just go away like that. All right, moving on. Acetone, H2SO4, a sugar. This is just syndiol protection. Okay. Oh, okay. So either, I think I meant for the step 2 answers, or I just said a brain fart. But syndiol protection, the stipulation is it has to be cis. So these two are cis, so these could potentially cyclize. But these two are also cis. And actually also these two are cis as well. So you can kind of see it gets kind of go crazy very quickly. But generally speaking, the 5-membered ring predominates. So as long as they're cis, it can form. So we'll have this cis-membered ring here. And then we'll also have this cis-membered ring here. Okay. So those 5-membered rings will predominate. You can actually also get the 6th-membered ring with these guys here. So these guys can form a 6-membered ring. It's totally possible, but it's 6-membered, right? So 1, 2, 3, 4, 5, 6. So generally this takes a little bit longer, but it is a bit more stable. So it is a possibility. But I would say for you guys, just to know that these guys form here. I apologize for making it hard to draw to you, just because that alcohol kind of gets in the way, right? Cool. Now, a couple of you might be wondering, does the center here epimerize because it's an acid? To be honest, there's no water. So I wouldn't say that it would, but I guess it could. I would say that if on the exam you were to epimerize here, you would be totally within your rights to do that, and you can get away with it. You can just say that it's an acid that's pulling out water but adding it right back in, right? Because I mean, again, you don't know, right? Yeah, cool. So I would say the 118C with helix answer is these two, and then this is if you're extra cracked, right? You would put this one, but it's okay if you don't. Cool. All right. So that's PGP. Mechanism, pretty simple, right? Anion, boom, boom, boom. Not much to think about. This would basically happen here. I engineered this so that it wouldn't collapse right back in, so you have to worry about that. And then this here is just, right, plus, get rid of it, form that carbonyl kind of thing, and then OME can attack from here, right? So nothing too crazy there. It's pretty easy to figure out. Cool. All right, syntheses. So we're going from this sugar to this lactone. We kind of should know where lactones come from. And if I kind of cut here, right? 1, 2, 3, 4, 5. This is 5-membered. Right, so 1, 2, 3, 4, and then 5. Right. You can kind of see where the sugars OH should go for the most part. Maybe we're not too sure about where this goes for the milk type being, but I'll just put it there. This just comes from Br2H2O, and this is just heat. So this here, okay. So what you want to notice is you're going from 1, 2, 3, 4 to 1, 2, 3, 4, 5. So this is just Kiliani-Fisher, which I'm just going to kind of annotate here. If I were you guys, I would draw out every single step and its product just to be safe. But this is what this is here. Okay, so technically there are 3 arrows worth of things you should have here, which means that this is actually epimerized. We don't know where it is. I should have mentioned that this is epimerized. My bad. But whatever. It's all good. You wouldn't have need to know that anyways. Cool. All right. So pretty simple. Not too crazy. All right. This here. Oh, I think you guys should kind of see where this is going. I wasn't exactly creative about this, but we have ester, we have ketone. couple different ways that we can go with this. Maybe we could even just start from here. Maybe we feel comfortable breaking down that ester, or that lactone, I should say, right? And so we have this. Okay. We have a beta keto system with an alkyl chain. This alkyl chain is specifically 2 carbons and an alcohol. So that to me tells me epoxide, right? So base and then epoxide. Okay. And now I have, it looks like, and beta keto ester, which I can alpha beta cut here. And then say that I have this ester here. And this here. Okay. So a little bit uncomfortable. Not the happiest with this, but again, if I think about this, if I draw this out, this is a 5-membered ring. So technically, I mean, this ester couldn't really like you couldn't really form an enolate and do any attack. It might mostly be this guy, does the attack. So not the happiest with this, but I mean, we can get away with it, right? And so now when I look at this, I have an ester going into an ester. So if I had to, guess on this, possibly we had the beta keto ester at this position here. Or sorry, the beta diester here. Okay. And so in fact, well, if that's the case, then actually this will be, yeah, okay. So this actually would have been the acid then. Did I tend to do this way? I don't think so. Now I'm trying to wonder about what I was thinking when I was writing this. Because now that I'm doing this, because if this is the case, then actually this would have been so this initially, this is fine. Okay. So then initially this would have been OH because it decarboxylated. And we form, let me do it this way. Right. So this would have been an OH. And so what I'm thinking is you're doing the ring thing here. Would I do that twice? Why would I do that twice? Oh, wait, no, that's not what I did. Okay. So, I mean, this is viable. So I'll just finish this out. I see what I did instead. All because I decided to do that. I shouldn't have done that, I don't think. That kind of threw me off my little vibe here. But anyways, yeah, anyway, so this one's just a bit weird, but you could do the thing where I just talked about, where you kind of add the ring here, decarboxylate, right? Reesterify, and then do your Clayson, right? Do that, that's fine. Retro takes you this way, it's fine. So this is an acceptable answer. But if you kind of actually just start here, okay, and say that you do this like ester step here, where this one attacks here, that's totally possible. Then it's just a matter of having the beta ester here, right? The one that's there from row 4. And now it's just a matter of, oh, you added in the epoxide. Okay, so you added in epoxide, closed it, decarboxylated, and then, did another Clayson. So not I mean, I should have written a better question, I guess, but, I was just kind of writing things up there in the morning. Cool. All right. So those are those two. Hopefully, again, those kind of illuminate some thoughts in your head as to what you can do. Moving on, another Gymtasia Pharmaceuticals. I wonder how many guys tried the other one. The other one was the first Gymtasia Pharmaceuticals was a good problem for midterm 2. But anyways, gotta figure out what this sugar is. So it's a tetrose. So 2 here. We don't know if it's a ketose or an aldose actually. So I guess all we really know is this much, but there was bubbling when it was digested. Sorry, someone knocked on my door. Just had to talk real quick. Anyways, but there was bubbling when digested by HIO4. So I don't remember if I mentioned this, but bubbling would indicate a gas escaping. So if you think about the products that can arise from HIO4 digestion, think about which one would have a gas in it, whether it be ketose or aldose. The answer is going to be ketose, right? A ketose, the gas that's evolving, is that CO2. So that's the trick there. So we need to figure out where this is. Okay, but if I do NABH4, oh, okay. So I've actually given the opportunity that you can just go ahead and guess, right? Oh, actually, no, never mind. I have not. Sorry, it's NABH4. So either for this, we form this. So you get the alditol. You're still unsure as to what this guy is. Oh, actually, no, I tell you the zero optical rotation and non-zero. So never mind, you do know where this is. Not bad yet. Okay. And then just COH it on that. I just don't want to draw it, to be honest. I don't want it to finish this. I mean, I kind of have finished this in 20 minutes. So it's kind of funny. So what that tells you then is that this had to be here, right? In order for this to be non-zero and this to be zero. Oh, well, oof. Well, now I guess I didn't design this great, did I? Yeah, I didn't do a very good job here. Okay, because it actually depends on whichever one you draw in each one. Okay, oversight on my part. Not the greatest question. So, because I can see how if you drew it where this one, like, because I kind of just guessed, right? I guessed that it would be OH here and here. Yeah, because if you do this and then you're gonna think it's that. Okay, okay, not the greatest problem. I will admit that. That could have been written better. Okay. I tried. I'm not Emil Fisher. I apologize. But you just take this and COH it, take the COH it, right? Yeah. Oh, wait. No. I'm an idiot. My bad. No. I am Emil Fisher because I put D here. So it's always, oh, there's only one. I'm an idiot. This is the only D tetros possible. I'm actually an idiot. Okay, my bad. Never mind. This is totally fine. D tetros. This actually gives away what it is, right? It's this. So that's the D tetros, and then okay, never mind. I'm just stupid. Okay, no, I'm just tired. Is what it is. It's okay. We're almost done. Cool. All right. Moving on. Not going to talk anymore about that. Blank is responsible for why sugars optical rotations. Make sure that's mutual rotation. Sucrose is a disaccharide of glucose and fructose. Subunits in a. I don't actually remember this. I'm just blanking. Yeah, I'm not sure, but it's whatever. Just look at your notes. Draw the furanose of beta D galactose, C4 epimer. To be honest, I don't really want to do this, so I'm actually going to skip it. I don't want to do it, to be honest. Circle the D sugar. So there's 3 ways to figure out a D sugar in the ring form. Okay. The first way, if on the sugar, on that clockwise carbon or that last carbon, there is a CH2OH, if the CH2OH is up, it's D. If it's down, it's L. Okay, so you want to look at that counterclockwise carbon. If there's a CH2OH and it's up, it's D. If it's down, it's L. Okay, there's none here, so this is not going to help us. There is a COH, CH2OH, so that's not going to help us. There's nothing here, and there is a CH2OH here, but it is down. So this is actually an L sugar, so we can just get rid of it instantly. Okay, cool. So that's the first thing you can look for. The second thing you can look for, if there is a chiral center on that chain. So let's say that there is a chiral center like this. If that center is R, it is D. If it is S, it is L. Okay, so just chirality sake. So nothing here and nothing here, but there is that chiral center here. OH is always 1, ring is 2, CH2OH is 3, 1 to 2 to 3. This would give me an R line, but the H is in the back, right? So sorry, the H is in the front. So this is actually a counterclockwise line. This is actually L. So this ain't going to be it either, okay? But if it were R, it would have worked. So now all that's left is the last thing you can look for, and that's when this carbon's empty. When it's empty, you look here. If the OH is up, okay, it is L. The OH is down, it is D. So this has a down OH, this has an up OH. This is our D sugar. Okay, so those are the 3 tricks. In the open ring form, right, it's whether this is on the right or on the left. That will tell you DRL. Cool. All right. Cool. And then that's it. All right. So that's the 2 midterms. I know I went through these really fast. I apologize. It just, it's late and I didn't think it was going to take this long. I think it's 2.5 hours, but that's both midterms. So I have nothing to worry about now. If there's any questions, just let me know. Yeah, cool. I am writing a third one for fun, as always, but it's, again, just for fun, so don't take it seriously. Actually, I think kind of show you guys some of the things that I put on it currently. So I make these in ChemDraw. This is what I have currently. I'm still researching some predictive products, but I've got like this here, which I should change that. I don't know why I wrote this one. That looks a little boring. If this is a fun one, very, very fun one here. This here. That one's a fun one too. Yeah, it's just cool problems. But yeah, cool. All right. Well, anyways, if any questions, let me know. Give us up a good one. I'll see you later. Good night.